Okay, can you hear me well? Once again, first time with a mic. Awesome. So I'm Vanessa Mercea. I come from the Technical University of Cluj-Napoca, and today I will be talking about one machine learning enhanced approach for sunquake detection in acoustic emission maps. So sunquakes, they have recently become more popular, but they have been discovered since 1998. So there are multiple definitions depending on whether we are looking at images or the theoretical definitions. So we define sunquakes as perturbations within the sun that lead to seismic emissions on the surface. And if we are looking at the image, we define them as circular waves that we observe on the photospheres that we associate to solar flares. Now, they are quite rare. So we have about 2 or 3 per year on average. Without machine learning, we had a couple of techniques that we could use to detect sunquakes, but they often were laborious, and they do need the trained eye of those few people in the world that are familiar with detecting sunquakes. Also, with these approaches, we are not always sure where to look and when to look, because we do know that sometimes they are associated to flares, but not always, so we don't have a pattern. Moreover, multiple methods do render different results. So we have movie method, we have time distance, we have helioseismic holography. With our approach, we relied on helioseismic holography. Now, with machine learning, we want to definitely reduce the manual work. We want pre-processing to stay intact with the helioseismic holography. And on the other hand, we do need some compute power to obtain this. And we do need to get a level of trustworthiness. Now, let's go through the data. We took solar cycles 23 and 24, so going from 1996 to 2011, and we used the holography method pre-processing to obtain these acoustic emission maps. Now, these are characterized especially by having a dark spot, usually in the center, which is the active region, actually. Now, in this dark spot, sunquakes may be detected manually, and they are detectable or seen as an increase in the intensity of a portion of pixels, as we can see here, over a duration of 8 minutes. Now, this is a simple example. We see the sunquake clearly. Here we have a much more difficult example. If you have to zoom in to actually see the sunquake forming here. So definitely this data set comes with a set of challenges. First of all, it's very unbalanced. So we have around 10,000 data points, and 4% are sunquakes, so a great imbalance factor. Secondly, the data is quite complex, so we have data points that have active regions that are quite large and positioned in the center, and others where the active regions are small to the side. So not consistent. Moreover, we have some fake signals that are generated from the holography method. So we have some light spots that seem to be sunquakes, which are not sunquakes. And lastly, the data set has not been used with machine learning before. So this is our full approach. We started with Dopplergram data that we downloaded from JSOC. We applied holography method. We constructed a data set that is published on Kaggle. So if you want to play with it, please feel free to do that. Then on this data set, we performed a set of augmentations, and this part is very important because it had a great impact on the results. And then we applied 2 different types of models. First, we applied temporal detection models to detect the start and end time of the sunquakes. And then we applied object detection models to detect the actual location of the kernel. And finally, we used additional data to validate whether our results were reliable. So, as I was saying, 2 approaches: predicting time first, predicting location second. So for predicting time, we have used contrastive learning. Now, if you are not familiar with this, the goal with contrastive learning in our scenario was first, with the unsupervised version, to learn patterns from data, so feature extraction. And secondly, with the supervised version, of course, to actually predict when the sunquakes started, when the sunquakes ended. In terms of methodology, with contrastive learning, what we are trying to do is we are trying to minimize the distance in the embedding space of our models between samples that belong to the same class. So as we see here, we try to bring positive samples together and negative samples together and try to push apart positives from negatives. So this is the thought behind this type of machine learning. Now, in our approach, we also use additional techniques. We use mode to augment, to synthetically augment our data set because we have a great imbalance factor. We used different classifiers, including SVC. We used custom augmentations, which I mentioned are very, very important. So let's move on to these. Why I say these are very important is because we tried going with the standard way, like the typical transforms that you see in computer vision, and they didn't work at all. Our models didn't converge, so we had to try to go custom. So these are generic geometric transforms to support diversity. So we rotated and flipped our data, our images. These are common, but then these three are custom made. The first one is used to enhance the signal of the Sunquake. So we apply a low-pass filter and then we solarize. So what this gives is this effect where you see pixels that have high intensity are enhanced, as we see here. Of course, even other points are enhanced, which are fake signals, but we don't apply this transform to all data points. We randomly apply it. So this helps a lot during learning. Secondly, we use this time-based mixing transform. As I was saying, Sunquakes do need to last for 8 minutes. So we need to enforce sequence information to our models. We have not used LSTMs. So what we did, we introduced this type of transform where instead of feeding our model with one image at a time, we fed it with 3 consecutive images mixed into one. So each sequence of 3s. We showed that our models showed to perform really well in predicting the starting time and the ending time of the Sunquake. So just the transition into and out of a Sunquake after adding this transform. And lastly, random erase. We use this instead of random crops because using random crops would mean losing the label information. So if we were to crop this area, we would lose the Sunquake information which was here. This is more forgiving. Okay, for predicting location, we didn't customize this a lot, so we have used one prototype of a faster RCNN model. So the methodology with faster RCNN models is we take the input image, we pass it through a series of convolutional layers, we obtain some feature maps, and then we have this network which tries to identify regions where there might be Sunquakes, and then a classifier on top which classifies whether the identified regions do contain Sunquakes or not. So this shortly. For results, we have 2 models. So this relates to the previous presentation. We have one model which has a shuffle bias. This means that we have the same AR, shared AR between train and test, which shows great results. And then we have a second model that has no biases. So the second model, which has no biases, is really good at predicting marginal frames, as I was saying. And this is caused by the custom transform that we have used. Okay, so let's move on to the fun stuff. After testing our models or validating our models, we had this post-validation analysis on uncertain data. So we chose some uncertain events, difficult events that were difficult for the researchers that I have worked with to mark manually. We applied our models, and we filtered the results. So where contrastive learning would say, hey, there is a Sunquake here, we applied the OD model for extracting the location. And finally, we used additional data. Thank you. And finally, we used the additional data from SDO for validating our results. So what we see here, we applied our model to 2 events. And what we see is the frames corresponding to the predictions from the contrastive learning model. So the frames where the contrastive learning model said there is a Sunquake here. And what we see with the CN box is the location predicted by the object detection method model for these particular frames where we had a positive result from the CL. We look at the IA94 channel, and we find that there is a flare here going on. And this is a very small flare. This is a C1 class flare. For one event, we look at a different channel in Aya, because this is a stronger event, a bit of a stronger event. But for both events, we do find the flares at the exact locations. So we performed a statistical analysis on this, and we found that both C1 flares are accompanied by sunquakes. And we see that both C1 flares are 4 sigma above the noise threshold. And if we were to look at the 24-hour interval, we would also see a statistical significance for these particular flares. Now, what's really cool about this is that these are the smallest flares associated to sunquakes that were ever detected. So I think the smallest until now was C7, and we got class 1 right now. Thank you.
Well, thank you very much, Vanessa, for keeping in time as well, and the very interesting presentation. Questions or comments? We have time. Over there in the back.
That was a great talk, thank you. What do you want to do once you find all the sunquakes?
Once we find all the sunquakes?
Yeah.
I don't know if we can find. Well, our train of thought right now is how to decide on which data to run this. And of course, we still need to work on doing some more statistical quantitative results, because we have these two, which is definitely maybe not enough for the physicist community, me coming from a computer science background. But what do you have in mind?
Oh, I'm just wondering, I don't know anything about sunquakes.
Maybe more people will become interested now.
Thank you.
By the way, I have the code base here because I had a workshop recently at a university. So if you want to check it out, you can go through the whole, at least inference process with it.
There's another question there.
Thank you for the talk.
Thank you.
I was impressed by the results. How could you reach kind of 0.9 accuracy on such a dataset which is highly unbalanced, actually? Did you use this mode technique both on validation and training, or only to train tests, and then you validate on true data?
We validate on true data, so we apply SMOTE only when training. But this has been a 2-year research, so there's been a lot of trial and error, definitely. We also use class weights on the contrastive loss function as a side, but I think for imbalance, just these two, just SMOTE and class weights.
Okay, just to give you an idea already, how big was the dataset and how much positive?
10,000 images and 4% positive.
Cool, thank you.
Thank you.
Another question there.
That was an interesting talk. So do you see sunquakes associated with other phenomena on the sun except solar flares?
I think Alin, he's the physicist I worked with. He may have a better answer than me. Can you?
For this particular work, we just focused on sunquakes and associating them with flares. We didn't look at anything else yet, because we were focused mostly on for the online people. So we were focused mostly on actually being able to properly detect sunquakes, and that means applying the holography method. So the machine learning application is a very particular application of on the holography data set, which is very hard to obtain in a sense. So it's hard then to relate back to a standard SDO image and relate to other phenomena, for the moment at least.
Yes, actually our dream, but we think it's very far-fetched, is to be able to apply these methods directly to the Dopplergrams instead of applying the intermediate holography method. But it's very far-fetched for now.
Yeah, I was just going to make a comment that have you thought about training a full end-to-end deep neural network to both do the holography method, but also to do the soundquake detection? Because a lot of deep neural networks show that multi-class or like doing more than one job actually improves the network efficiency. So doing the inversion from your input data to your holography output, but also detecting soundquakes could actually be a very good approach.
So could you please repeat the last part? Doing a version of? I'm curious.
So basically, just basically training a deep neural network to do the holography process from your input data, but to also do the detection of the soundquakes. So one network would do both processes. Because multitask learning is, I think, what it's called.
We have tried applying autoencoders for reconstructions, so they worked really bad on this data. I'm scared that we might not be able to reproduce the holography method for now. I think that's a difficult task on its own. Thank you.
We have one question online, so could you please go ahead?
Yeah, Vanessa, it's not more a question, it's more of a comment. And thank you, Vanessa. I enjoyed your talk so much.
Thank you.
Yeah, we need a tool like this. We needed this for years, and I'm happy to see this is now working. Responding to one of the questions that the audience asked about whether sunquakes have been observed in other solar events, they haven't, as far as I know, and the look for sunquakes have been really biased towards solar flares with high emission in high X-rays or big flares observed by or classified by GOES, by the GOES flux. Some comments or just suggestions you may include in future works is to include more input data. You mentioned that you have used the helioseismic maps, the output of the helioseismic holography. And those maps come into determined frequency bandpass. So I assume you choose a particular bandpass, I don't know which one. You probably want to train your models using several of those frequencies, acoustic frequencies. Sunquakes are also visible in movies of the differences of Doppler maps, so you could also try to do that. And you mentioned your dream of applying a machine learning method directly on the Doppler maps, so this may be a way. And of course, in the in the time distance plots. Also, since, and here comes the physics-informed learning, the sunquakes that the community has found so far, all of them have been found in the penumbra. So you may also try to look into those regions, although that's also kind of biased the search. One question that we have had for decades now in the community is whether you can find sunquakes outside active regions. And a technique like this would be really helpful for that. So thank you, Vanessa, for sharing this.
Thank you. Thank you so much for all the comments. Thank you.
And let us thank Vanessa again for the interesting talk. Thank you.